Swayam Prabha. Digital India. Educated India.
Welcome to the class of intelligent product design. In the last class, I have talked about lag compensator, and today I will talk about lead compensator. So, these are all classical type of compensators. Also from here I will talk about the PID compensators. Now, all these compensators, where do we apply? Well, in terms of the intelligent product design, there are different applications. For example, engine control is a very classical field where all these type of controllers can be applied, and there can be many parameters here. For example, you can have input parameters like fuel flow, which can be directly sort of interlinked with the thrust that you are generating, the stator vane angle, the metal temperatures, nozzle area and the flows. So, this kind of input output relationships, if you want to establish one-to-one correspondence of them, then you can use the classical control system. If of course, you want to control all three of the parameters in one shot, then we have to go for state space control. So, these are typical applications, and another important thing that I want to tell you is that where does the controller go in the circuit, right? If you remember that we have talked about a gain K earlier, and we have talked about the plant G earlier. Now, this gain K is something that was a constant value that can be changed, but in this case when we will talk about a lead or lag compensator design, we will make it slightly more complicated. So, it will become K S plus A over S plus B. So, that means the system can have a 0 as well as a pole, and all these things comes not in the feedback loop, but in the forward loop. So, this part is the forward loop. Okay. So, this part is the forward loop, and I have simply kept unity gain. So, this is unity gain in the feedback loop, unity gain in the feedback loop. Now, there are some controllers which can be also used in this loop, but in this time I am keeping everything in the forward loop, keeping in mind that this part, that whatever is unity now, is corresponding to the sensors. So, this part is related to the sensors. Now, there are different types of compensators that you can design for such a system, like lag compensator, which I earlier talked about, lead compensator, which we will be talking about today, and using both of them together is called lead lag compensator. And also there is something special that can be used, it is also called notch filter. So, let us see that what will be the lag filter compensation design. Now, in the case of lag filter compensation design, we will be introducing a set of pole and zeros, just one pole extra and one zero extra. Overall, there has to be a reduction of phase in the system, that is why it is called lag. Okay. So, at this point I also want to tell you that suppose I have in the compensator something like S plus Z over S plus P, Z stands for the 0 of the transfer function and P stands for the pole. We have to always keep in mind that zeros give phase lead and poles give phase lag. So, that means once I am talking about a lag filter design, the poles are to be more dominant than the zeros. Okay. So, how can we say that a pole is more dominant than a zero? Well, if you look at the S plane, let us say this is the real and this is the imaginary, then you would see that if a pole is closer to the origin in comparison to the 0, if a pole is closer to the origin in comparison to the 0, then this is called a lag compensator. On the other hand, if I parallelly draw another diagram in which in the S plane, same S plane, the real versus imaginary, and there if I have a 0 which is closer to the origin and the pole is away, this combination is called the lead compensator. So, this is what we have seen in the last class. So, now this is the lag compensator where the pole is closer to the 0 and then it becomes more dominant. What will be the use of this lag compensator? Well, first important point is that it improves the steady state performance, because if the pole is very near to the origin and the 0 is little away in the left side from the pole, then from the uncompensated situation where you do not have the compensators, if you add this compensator which is ZC by PC, we will be able to see what will be its effect in the steady state performance of the system. So, let us go to the lead controller part, because the steady state performance improvement that we can gain from the lag compensator system is something for which you have to provide a kind of a unit step input to the system. And then, so let us say if I keep a unit step input to the system, so something like a unit step input, okay, with respect to time. So, this is time and this is amplitude, and we give a unit step input as a reference signal. Okay. So, in the steady state performance improvement when I am talking about, so that is telling how good the system will be able to follow this command. Okay. So, if I do not use a lag filter, many a times, let us say my transfer function is something like S plus some 5 over S plus say 3. Okay. Now, this is clearly a transfer function in which there is no predominant pole closer to the origin. Okay. So, this system would not be able to follow this command. Okay. So, you may see that it will slightly fall back, okay. It will not be able to. On the other hand, if you now actually integrate these lag combination, something like let us say S plus 0 is far away. So, I can still keep some S here, S plus 7 by S plus 0.01. Okay. Then, if you look at the response of the system corresponding to this, you would see that it is almost going to sort of follow the command. So, that is what is called the steady state performance that the command will be able to follow if you can create a lag system. So, that is whenever we want a system to suddenly shift from value A to value B or position A to position B, we use the lag filter. Now, let us look at the lead filter, that is what we will be talking about. So, the lead compensator is similar in structure like the lag compensator, only thing here the 0 will be dominating. So, which means that the 0 will be much smaller than the pole. Okay. So, that is something that we have to keep in mind. So, that is what I said, that the B is to be greater than A, of course, in terms of their absolute value, because both of them are appearing in the left hand side. Now, remember, if a pole or 0 is closer to the origin, it becomes dominating, and I already told you about it. Now, lead compensator, what is the application of it? It improves the stability of a system by shifting the root locus towards the left of the origin, so that the lead compensator can create a much more stable solution. So, while lag compensator improves the steady state response, sacrificing the stability, lead improves the stability of the system. So, both of them work for certain very specific purposes. Now, let us look into the design of a lead filter. So, consider a plant which has 3 poles 0, -4, -6. So, that means if I again draw the S plane. So, if I draw the S plane, So, this is my real of S and this is my imaginary of S. Then I have already 3 poles here. Okay. So, this is a type 1 system, one pole is at 0, another pole let us say is at -4 and another pole is at -6. Okay. This is what the plant is having and it is definitely a third order system. So, this plant I can also write it down and there is no 0 in this system. So, that means the plant transfer function can be written as something like 1 over S into S plus 4 into S plus 6. That is the uncompensated transfer function. Let us say that I plant transfer function which is a third order system, we can clearly see, but because one pole is quite far away it may still behave like a second order system. So, if I look at the step input response in another side, so time domain and then the step input. Okay. So, I am giving a step input to the system. So, what I am going to see is that it will behave like a second order system predominantly and then it will behave like this. Okay. So, that means gradually it will be able to follow the system step command or the reference signal. So, this is the reference signal. Okay. Now, there is an overshoot always there in the system and this overshoot which is the percentage overshoot at this point, let us say I want to reduce this overshoot. So, objective is get 16% overshoot. So, this is the overshoot of the system. So, I need to reduce the overshoot to 16% with 3-fold reduction in the settling time. Now, what is the settling time? Well, settling time is when this amplitude comes down from this. Okay. So, within say with respect to the reference signal, let us say plus minus 2% of the value. Okay. There are 2 ways to define, some group uses plus minus 2%, some group uses plus minus 5%. Okay. So, settling time is this time. Okay. So, this is what is the settling time Ts and it is generally written as 4 over zeta omega n, okay, where zeta is the damping and omega n is the natural frequency of the system. So, this settling time is to be reduced 3-fold, that we have to keep in mind, and the overshoot should be less than or equal to 16%. Okay. Now, overshoot is directly related to the damping ratio. So, there is a formulation for it which will give you that 16% overshoot is equivalent to zeta as 0.504. So, that means this zeta value is 0.504. Okay. And then with this zeta value, if you look at the chart, you will be able to get this and then you can now find out that at that value what are the location of the poles. Okay. So, if you draw a root locus diagram, you would see that with these values, so that means this is the 16% overshoot. Okay. Damping ratio typically represent this angle. So, 16% overshoot, that is my limit and that is going to give me the poles like minus 1.2 plus 2.06 and this point here as minus 1.2 minus 2.06 J. Damping is 0.503 which is overshoot is 16%. Corresponding natural frequency is 2.38. Now, keep in mind that this is different from when it was a completely open loop system like this. Okay. So, already I have assumed a closed loop system and the closed loop system is already giving me an overshoot of 16%, that much is there, but it is not giving me with corresponding to this value. If I now figure out what is my Ts as 4 over zeta omega, I know the zeta value is 0.503 and natural frequency I can find out from this position corresponding this distance and it will come out to be 2.38 rad per second. So, I can get a value of the settling time, but this settling time is to be further reduced by 3 times, 3-fold reduction is what we have to do and for that we have to design the lead filter. So, that is the point that we have to do. So, let us see how we can go ahead with it. Okay. So, this is the chart from which you can either use this formulation or you can use a chart in order to figure out that corresponding to 16% overshoot what will be the typical value. Okay. So, for us we have figured it out already, this particular value. Now, let us look into the step by step process. Okay. As per the design specification, at the current location where you have 16% overshoot, you have a settling time value Ts as 3.33 second. Now, you can recheck that whether the system is behaving as second order system. That means, where are the poles here? So, 2 poles we already know where it is, the third pole should be quite far away, that is all that we need to do in order to recheck it as a second order system. Now, what is the settling time? 3.33 second, but I have to reduce it 3-fold, that means it should be 1.107 second, and for 1.107 second the corresponding the real part will be 4 over Ts, that will be 3.613. So, if I want to keep the same damping, then where should be my placement of the poles? The omega d value then should be 3.613 tan of 180 minus 120. So, that is what is the desirable value of the omega d, which is at 6.193. So, that means the desired poles are to be shifted. The desired poles are to be shifted such that it should be at minus 3.613 and the j value is plus minus 6.193. Now, if I put this desired value, okay, where, so I already have poles here and a pole there, that is the system, and I already know that if I have to reduce the settling time, then I have to add a pole whose real value should be something like 3.613. So, this value should be 3.613. Okay. And also I know that the j value should be 6.193, but the moment I add this pole, my root locus has to pass through this pole. So, the phase condition has to be satisfied. So, if I try to measure the phase due to the inclusion of this pole, I would say that if the root locus has to pass through this point, the phase will be minus 275.6. However, a pole cannot have it is to be part of a root locus, it cannot have anything other than odd multiple of 180 degree. So, that means the nearest compensation in order to become minus 180 degrees 95.6 degree. So, I have to add 95.6 degree angle with this minus 275.6 degree, so that I can get the overall phase contribution by this pole and 0 as 180. Okay. Now, keep in mind that this 0 is slightly ahead of the pole, that also it is a lead filter. So, 0 should be more dominant. So, my 0 should be somewhere here, so that it can give an overall angle of 95.6 degree. And then the compensator 0 will you can then find it out graphically, and you will get it as minus 4.22, and compensator pole you may choose at minus 20. Okay. So, if I do like this, so once I get the minus 4.22, then I can actually simply multiply it by 5 times and keep the corresponding pole somewhere here. Okay. So, it is far away minus 20, so that it does not disturb with my system. So, that is how I can design a lead filter for the system. Now, what will be the effect of this lead filter? If I try to plot root loci of the compensated and uncompensated system. So, this blue line is the TF1 of the system, which is uncompensated, and the green line is the compensated system. You can clearly see that the green line is away from the blue line. That means, it is going towards the left, which means it will be a more stable system. So, that stability is what we have been able to bring to a system with the help of the design of this lead filter. Now, I also at this point want to tell you is that instead of a lead filter, we could have achieved the same thing with the help of a proportional and derivative compensator, which is also known as PD compensator. So, suppose I take a plant which is like having one pole at the origin. So, it is a 1 over s into s plus 1. Now, instead of a lead compensator which can be something like k s plus 2 into s plus p, and then you know that if it is a lead compensator, then it is the 0 which has to be more dominant. So, the pole has to be far away from the 0. So, let us say I take it 5 times away, so that it is 10, or 10 times away, so that it is 20. So, like that I can put these, and then I can see that what will be the root locus of the system. You would see that if the lead pole is at minus 10, then this is the way the root locus behaves. Okay? Starting from the two original poles that you have, one at the origin and one at minus 1. But if you further keep the pole away, then you would see instead of going to infinity, the pole is actually coming back here. Okay? That is the way it would behave. Now, if you compare this with respect to a PD controller, which is simply k times s plus 2. So, there is nothing there in the denominator. You would see a PD compensator will give you a perfect circle. So, in comparison to the PD compensator, the lead compensation is slightly distorted form of circle, but you can actually control that circle by having a pole which is farther and farther away, because this is with 10 z. You can go for 20 z, 100 z, and we would see that this will gradually approach actually this particular circle. So, this circle of PD is the limiting circle, and this is what a lead compensator at an extreme case is going to approach. So, that way PD and lead compensator are basically very much similar, and you may say that proportional and derivative controller is a special case of lead compensator. So, you can try this type of a problem, that considering unity feedback of a system, find out the lead compensator such that the maximum overshoot is about 20%. Earlier I had done it for some other overshoot value 16%, now it is 20%. So, you can find out what is the corresponding value of the zeta, and however, the settling time now has to improve by a factor of 5. So, follow the same procedure and see how you can design a lead compensator. Now, how do I practically realize such lead compensators? Well, you can actually realize both lead and lag compensator with the help of some resistors and some compensators. So, this is the complete system that you can actually use. That means, you have one resistor and one sort of a capacitor in parallel, and then the entire thing is in series with another resistor. So, this kind of a circuit can be a lead compensator circuit, which is a completely passive circuit. If you want to go for PD, you on the other hand have to design an active circuit. The difference between active and a passive circuit is, passive circuit does not need any additional power, but active circuit will need an additional power. So, that we have to keep in our mind. Now, with all these knowledges, you can also try to develop a controller which will be little more complicated, because I told you that suppose you have a case where you have to improve both the steady state performance of the system as well as the stability of the system. Then you have to go for a compensator which is like lead lag compensator, or a compensator which is like a PID compensator, where P stands for proportional, I stands for integral, and D stands for derivative control. So, here you have a PID, and then this is a plant. So, you can sometimes write it as PS, but better to write it as GS. Okay. So, now the plant is controlled by an input E, and this input in terms of PID controller is having a proportional element Kp times Et, that is the error input. Proportional to it, you are actually giving an input, one part of the input U, another part is integral part of Et dt, another part is Kd E dot T. So, that is actually related to the rate of the error. So, in the frequency domain, this will look like what? The integrator will become 1 by s. So, it will be k I by s, and the differentiator will be k d s. So, now if I try to find out the input output transfer function of the system, remember many times we write it with different notations, but it is the same, that it is the compensator times the plant. Sometimes we write it as something like say the compensator is C. So, C s and then the plant is, let us say, G s. Okay. This is corresponding to, of course, unity gain in the system, and then over R s. So, this will become 1 over C s G s. Okay. So, something like that will come up. Now, this is the transfer function of the system, where I can use for the C s transfer function this one that we already know. So, I can use this system. Now, what are the advantages? Let us see it. So, if I use only proportional part of the controller, I can adjust the output of the system, but sometimes it may cause instability. Okay. So, a typical case is something like when you have 2 pole type of a situation. If you look at it, that you have, suppose, 2 poles here, and suppose you have a 0 here. Okay. Then what will happen? Initially you are at this region. As you are increasing the gain, you will be actually coming towards this 0. So, that means the moment you cross this line, this is the imaginary of S, please keep in mind, and this is the real of S. So, the moment you cross this line with the higher gain, you would become unstable. So, Kp has this problem. For some cases it may cause instability. Ki, on the other hand, can produce 0 steady state error, that is good, but it will slow down the response and it will create instability also. Kd will provide a rapid system response. The only problem is, because it is a derivative type of a operator, it will be sensitive to noise and non-zero offset. So, that we have to keep in our mind. Now, if I try to apply a PI controller, so we can try all these variations, PI, PD, PID. If I try to apply a PI controller on a first order system is something like a thermocouple, like where you are measuring the temperature of a system and taking some intelligent decision. Or let us say it is a system where you are controlling the position of water table or something. So, in such a case, it is a first order system, because the denominator S is of degree 1. So, it is a denominator polynomial is in terms of the degree of S, it is 1. So, it is a first order system. Now, if I apply on this system a compensator like Pi, which is Kp plus Ki over S, so then you can actually write this whole thing in this manner, so that you can get 1 pole and 1 0, and you can write the complete transfer function now following what I have earlier written, and you will get this typical transfer function. See what is happening. Your system was initially first order. With the addition of this compensator, you have essentially become a second order system. So, that is something that you have actually increased the complexity of the system. That is a price that you are paying. Now, what you are gaining because of this? Well, suppose let us take a numerical example. Let us say I have a situation where gain k is 1 and t is 10 seconds. So, this is 1 over 1 plus 10 second is the transfer function. Now, if I give a unit step response, the controller will know where it is close to 1, it is maximum that it can go is close to 0.5. So, it will not be able to follow the signal. On the other hand, now if I use these kind of a system of a predominantly PI controller, then I can get the new transfer function. And if I look at the effect of this new transfer function, you would see earlier I was here, but now it is a second order system, even though I have overshoot, but I am able to follow this in the long run. So, that is something that I have been achieved with the help of the design of a PI controller. Now, let us see if I apply a PD controller on a first order system what happens. So, this is a first order system. I am trying to apply a PD controller, and then the step response is already not of our worry, it is close to unity. Okay. If I apply the PD controller, what I will see is that it is behaving much faster than what it has done earlier. So, here earlier in order to reach, let us say 0.9 value, it was taking 0.04 second. Okay. And now that 0.9 value it will take, okay. So, 0.9 value is somewhere here. So, it will take much smaller time in order to reach the same value. So, this is an assignment that consider a second order system with a natural frequency and damping, and can you find out a PID controller which improves the steady state performance 10 times and also improves the peak time 5 times. Okay. So, try to solve based on whatever we have discussed today. There is an important issue of tuning of PID controller. Okay. How do we actually set this? Well, that is something that I will talk about how to do it using Ziegler-Nichols rule, so that you do not do it just with the help of your manual tuning system. Okay. So, there are two sets of rules. First of all, you already know this transfer function of the system. First rule is for system where the exact dynamics is unknown. Okay. So, in such a case, you first play with the proportionality constant K0 and note down when the system would become second order, what is the corresponding time period. Now, once I know that, then I can choose for only proportional controller the tuning value to be simply 0.5 K0. For PI, the Kp value to be 0.45, Ti as 1 over 1.2 T0, and for PID 0.6, 0.5, 0.6 of K0, 0.5 of T0 and TD as 0.125 of T0. So, that the total transfer function for a PID looks like this. Okay. So, this is an empirical rule through trial and error, but it works very well. So, we can actually utilize it. Well, that is for an unknown system. If Ziegler-Nichols rule is to be applied for a known system, then I already know that when it will be unstable, because I can carry out a root stability analysis and find out the critical gain K0, and then I can use a similar strategy in order to actually tune the system. So, that is the way we can do it. Thank you.